Hello, my name is Robert Labonte. I'm a Principal Solutions Architect at Fastly. I'll be talking about using the power of edge compute to enhance streaming delivery. Why build dynamic edge applications? You may have a large library, most of which isn't regularly viewed, but you want to or need to implement new streaming features. For instance, Roku requires videos longer than 15 minutes to have a JPEG image stream. We'll also discuss lowering latency to improve viewer experience. In addition, we'll discuss converting on the fly all of the streams to be uniform, such as moving from HLS using transport stream to fragment MP4 CMAF. There's also a considerable cost savings when using edge computing because there's no need to remux a large video library where most of the content is seldomly viewed. You're only charged for what you use. Dynamic edge applications have these characteristics. The output of the apps is in CDN caches, not on storage. Content is dynamically generated just in time. The last two items are optional, but are definitely worth striving for. No modifications to the source. And stateless. You don't have to worry about a database or other server going down and affecting video playback. All the apps I'm showing today were built using Fastly's computed edge, using the Rust programming language, and rely on FFmpeg libraries when necessary. FFmpeg is compiled to WebAssembly, WASI, for Fastly's computed edge environment. These apps can all be built in other environments using other languages and other libraries. I have included command line FFmpeg instructions whenever possible. These apps can be built to be run anywhere, but edge computing offers many advantages over other environments, such as instant scale. You can instantly ramp up to meet traffic demands. You don't pay for idle capacity. And, effectively, edge compute is a supercomputer. We can encode thousands of JPEGs per second with that compute power using edge compute. The first application I'd like to show you is relatively easy to implement. This application is particularly useful when you have lots of long-tail content that gets few views that typically result in cache misses, or when your origin is far away from your viewers, such as when your origin is one continent but your viewers are in another. This optimization ensures content will be ready and near the viewer before their media client ever makes a request for it. No master manifest changes are required. In Rendition playlist, we'll modify segment URLs with pre-fetch instructions using query parameters. For segment request, when those query parameters are encountered, it triggers a pre-fetch operation in the Edge app. Here is a typical Rendition playlist. The file name of the next two segments are added to each segment's URL using query parameters. Because we're relying on query parameters, this is compatible with all existing media players. Take note of segments 6 and 7. We wind down the prefetch instructions because we don't want to cause a 404. Fastly's computed edge allows for continued processing after handling a request. This is a rare feature. Your chosen environment may require putting prefetch jobs into a message queue for a separate service to make a prefetch head request. Many CDNs convert head requests to get requests to origin and store those bytes in the CDN cache. The prefetch operation must be done in a manner that doesn't block the media client segment request, because that would degrade playback. This sequence diagram shows that the first segment is a pretty typical client to CDN to origin interaction. The media client is oblivious to the other actions happening behind the scenes. This is the first request the CDN has seen. Head requests are made for segments 2 and 3, along with the GET request for segment 1. For segments 2 and 3, the CDN caching layer converts those requests to GETs to the back end and stores those bytes. The CDN cache will then confirm 200 OK back to the Edge app. This is where the magic happens. On subsequent requests, we could see the optimization take effect. Instead of going to origin for the requested segment, it's a nearby cache. Segment 3, which had a previous header request, has an additional header request that is quickly returned by the cache when it confirms that it has its bytes. Segment 4 has not been seen before, so a request to origin is made to put it into CDN cache. Here's a curl request for segment 1. As you can see, it's a cache miss for that media segment. The request for the very next segment is now a cache hit due to the previous prefetch operation. This is a dynamic implementation of Roku's JPEG-based Trickplay. Roku's own tool uses FFmpeg under the hood, so the output files of this app will look no different. This app works with both VOD and live. This application is a little bit more involved than Prefetch. In the master manifest, we need to find a rendition playlist for video frames to be converted to JPEGs. We then insert links to dynamically generate rendition playlists. When requests are made for the dynamically generated rendition playlist, they are returned with modified segment URLs that include JPEG encoding instructions. And lastly, we actually need to convert a video frame to a JPEG on the fly when a JPEG is requested by the media client. This is a basic HLS master manifest. We have created an algorithm to select which playlist to use based off of resolution. Here, we've selected the 640 by 360 rendition. Its resolution is the same as our highest desired JPEG resolution. The dynamic playlists are links to the original playlist, but query parameters with JPEG encoding instructions added. Here's a simple rendition playlist. The query parameters of the rendition playlist are now appended to every segment URL. We've highlighted these in yellow. When a media client makes a request for the segment URLs, the Edge app will convert the first video frame into a JPEG and return it to the media client. Here's a sequence diagram showing the workflow. Because JPEG creation is compute intensive, we have caching placed in front of the Edge app as well. Subsequent requests for the JPEG will be served from cache. As you can see, when the media client makes a GET request for a JPEG image, when it hits the Edge Compute app, it gets converted into a GET request for the video segment. When the video segment is returned to the Edge Compute app, it decodes the very first video frame and then re-encodes it into a JPEG and returns that to the media client. Here's the FF probe for the video segment. Here's the output for the very same segment, but this time JPEG encode query parameters have been added. And as you can see, it's now a JPEG image. Roku's tool uses command line FFmpeg to generate JPEG images. For those who use command line FFmpeg for their workflows, I've included what an FFmpeg command line is needed to convert the first frame of a video segment into a JPEG. There are a few things to consider. The Edge app can only use the information provided to it via the segment request. If there's a map file in the playlist, its location needs added to each JPEG URL. FFmpeg treats the map file plus the video segment as a valid file. Failing to prepend the map file to the segment before sending it to FFmpeg will cause a decoding failure. If there's a byte range request, which is common in iframe playlist, you need to add the byte range to each segment URL. For this demo, we use query parameters that explicitly tell the encoder what to do. But in a production environment, we advise using predefined encoding presets so you don't publicly expose encode settings which could lead to malicious requests. Here are a few observations we've made while working with this application. Video decoding takes a majority of the processing time, up to 66%. Using lower resolution video source is faster. HEVC and H.264 have similar processing times. Using non-keyframes or accurately seeking the times is too compute intensive for just-in-time processing. This application can also be used to generate video preview images or any other images you need from the video. Moving on to stream format conversion. So you have a bunch of HLS formats floating around. The majority is old videos that rarely get viewed, so it's hard to justify a huge remuxing operation. But it's a headache maintaining these legacy streams, making sure your video players are compatible, and other problems. This app can make all of the content in your video library uniform. This works with live streams as well, so if you have an old but trustworthy live encoder that outputs MPEG-TS, you can still use it, but can now serve fragmented MP4 CMAF in place of transport stream. There are two options: keep the content mux or demux the content. This app will also work with content that's already been demuxed. Keeping audio and video muxed together is the easiest approach. It doesn't require modifying master manifest. If you want to demux audio video, new audio-only playlists will need to be generated. Similar to other apps, Rendition playlists are modified with query parameters. Here is a typical Rendition playlist. Like the other apps, we've modified the URLs to let the Edge app know it needs to convert these to fragmented MP4. If you're going to demux audio and video, you need a signal to the Edge app. I prefer using file name extensions such as M4A or M4V to signal whether it's an audio or video segment. But query parameters would also work. Also note, the map file in a demuxed environment, you must signal whether or not it's for audio only or video only. Here's a sequence diagram showing the cold miss. The backend cache is helpful if you're going to demux audio and video, since segments are needed twice, once for the newly muxed video segment and again for the newly muxed audio segment. As you can see, a GET request for the ISO media segment, whether that's fragmented MP4 CMAF, goes to the Edge Compute app, where it's converted into the MPEG-TS segment request all the way to origin. When that's returned, it's then remuxed on the Edge app, and the ISO media segment is returned back to the media client. Because that operation is compute intensive, there is a cache in front, so subsequent requests for the same segment will be served by the CDN cache. For those interested in trying to do this with command line FFmpeg, here's the command that converts TS to fragmented MP4. Please note, FFmpeg outputs both the map and media packets in a single file. For a playable stream, the map file and the media packets need to be placed in separate files. You'll also notice there's a bitstream filter is required to convert MPEG-TS compatible AAC to MP4 compatible AAC. So in conclusion, Edge Compute is very fast. These applications can work for both live and VOD. Because we're using query parameters, they work with all existing clients. You can use more than one of these apps at the same time. And again, using Edge Compute allows for instant scale. Thank you very much for everybody for listening to my talk today.